Thank you. Thank you very much for the invitation to participate in the Global Diagnostic Directors Conclave. And I particularly want to thank Professor Tupil Venkatesh, a great friend and a person whom I admire greatly for all his activities, for all his knowledge. And he is the president of our International Society of Chronic Hypoxia. Uh, uh, Thank you for the Foundation for Quality of India, that is changing the way science is evaluated in the laboratories throughout all India and beyond. So it is a wonderful moment for me to share with you. Please enjoy this talk. It's about the challenges in diagnostics at high altitude and in space. You may wonder, what is this doctor talking about? It is fundamental that state of the art medical laboratory diagnosis in high altitude and space research be developed. High altitude and space environments present unique physiological challenges, including hypoxia, radiation, and microgravity in space, which can alter human physiology and pathology. See here, sea level has a pressure of 760 millimeters, where you all are probably now. La Paz has at an altitude of 3,500 meters, 495 millimeters. That's the pressure we live in throughout all our lives. But space has no atmosphere, and hence the pressure is zero. So most spaceships now use 760 millimeters, the top level there, as at sea level. But this is wrong. They should use this pressure, 495 millimeters, the same as the altitude of La Paz. That's a level of chronic hypoxia that definitely the space travel has to be in this pressure in the future of chronic hypoxia. This is something I have proposed to since many years, and it's beginning to be understood in its importance. Conventional medical diagnostic tools may not account for these extreme conditions, leading to inaccurate results. Thus, advanced laboratory technologies are essential for accurate diagnosis and monitoring. You see, you have to build sturdy equipment to travel to high altitude and measure efficiently, and also to space, of course. Homeostasis at high altitude and in space is not the same as sea level homeostasis. Homeostasis refers to perfect biological function of your organism, and where you feel very healthy and effective and you can do exercise, think, and so on. That takes millions of reactions in your body permanently happening. This is the city of La Paz, Bolivia. At high altitudes, reduced oxygen levels can affect blood parameters, immune function, and organ performance. Standard laboratory equipment calibrated for sea level conditions may misinterpret data, risking misdiagnosis. And up there, at high altitude, is extremely important, but in space, it's crucial. The city of La Paz, Bolivia, between 4,100 meters to 3,100 meters, has more than 2 million inhabitants. It is a lovely city, and you can look at our mountain here is Illimani, this Illimani mountain right in front of our city. Now, let me explain that at sea level, the pressure is 760 millimeters. At the summit of Mount Everest, at 8,842 millimeters, it's 250 millimeters of mercury. That's 1/3 of the pressure of sea level. And to don this spacesuit, you have to have in space at 330 kilometers of altitude, where the pressure is zero, you have to have about a similar to Mount Everest pressure in order to breathe and survive. And so it's the minimal pressure that this suit can tolerate. So if you have to go from sea level to this suit when you put it on in a spaceship, you see you are changing 510 millimeters of pressure. That's why to get out of the spaceship and put one of these suits on, it takes many hours because it's a big pressure change. Whereas in the city of La Paz, we're at 495 millimeters, and in this beautiful city, we have 1/3 less pressure than at sea level, which means that if you had to start from the city of La Paz pressure, you would only be using, having to change to 245 millimeters of mercury, one half the pressure change. This is extremely important for space travel. And that way, biology takes care of one third of the pressure because we adapt to high altitude chronic hypoxia, and that becomes the starting pressure, the city of La Paz. So chronic hypoxia has to go up to space. It will. It definitely will. And not only in the spaceships, the EVAs, but also in the habitats. I'll talk about that later on. This is where we are, and this is where we intend to go. A place where there's no atmosphere, from an environment full of oxygen to where there is no oxygen. Chronic hypoxia is the first step in biospace forming. It is one small step, but actually a giant leap. Biology becomes a tool that bypasses the pressure laws of physics in a totally physiologic manner. So you may be wondering, what is this biospace forming word? Well, that refers to adaptation of all living beings on planet Earth to space, which we will do. Elon Musk is preparing to go to Mars and the moon, and humans need to go beyond Earth. They will. That's the evolution. And you see here, there's a paper. The first time I used the word biospace forming was in this article that I wrote for the BLDE journals in India. So India has the priority of the publication of this word. And when I finished publishing, I I realized I had not searched in the internet. Maybe the word already existed. So I checked, and you see there it was all blank except one citation for this paper of India. That was in 2018, by the way. Similarly, in space, microgravity alters fluid distribution, bond density, and cellular behavior, requiring specialized diagnostic approaches. State of the art portable and automated lab systems such as microfluidic devices, AI driven analyzers, and point of care testing tools are crucial. These technologies must be robust, energy efficient, and capable of real time analysis to support astronauts and high altitude researchers. You see, this is a high altitude pulmonary edema, a consequence of being at a low barometric pressure, rapidly ascending, and some people can present liquid in their lungs, like you see in that left chest x ray. And the right one is a chest C scan. Look at those lungs filled with water. Very complicated, similar to COVID. And I have a paper about that COVID in relation to high altitude pulmonary edema. Investing in such innovations ensures the early detection of conditions like space anemia, high altitude pulmonary edema, and the effects of cosmic radiation. It also supports long duration missions such as Mars expeditions, where traditional Earth based diagnoses are impractical. In this direction, HAPI IPA, our institution, it's called HAPI because it's High Altitude Pulmonary Pathology Institute, and IPPA is the name in Spanish, has taken a great lead at La Paz. Additionally, biosensors and nano technology can enhance detection sensitivity for biomarkers affected by extreme environments. Here are the hemoglobin values found at different altitudes in resident populations. If you see the X scale, it's the altitude. The Y scale is the hemoglobin. As you go up in altitude, you increase red blood cells. And so we estimate that on Mount Everest, the number of red blood cells, the hemoglobin, would go up to around 26 grams per cent. That was confirmed with laboratory studies because this is a trend prediction line. The distribution curve of the carbon dioxide, arterial carbon dioxide tension in 1,865 patients at our laboratory showed this distribution. As you know well, that acid base values of sea level for PCO2 are 40 millimeters of mercury. But here in the city of La Paz, it's 30. The average is 30. And what happens as we go higher? PaCO2 goes lower and lower. And when you reach Mount Everest right there, Mount Everest is this last point, the PaCO2 is around 8 millimeters of mercury. There's a curve. So you see the equipment has to be calibrated for different altitudes. This is a very interesting graph showing that we at high altitude can live longer. And on the left, you'll see the lower lands of Bolivia, 221 millimeters, and gradually we go up to different populations, all the way up to Potosi, the mining town located at 4,090 millimeters. And you can see that people that are older than 100 years can people more people live older than 100 years at the highlands. This is the sea level status for the pH 7.4 and PaCO2 40. As you go up to the altitude, the inspired oxygen tension drops, you increase ventilation, you reduce carbon dioxide, and you saw that on the graph. You increase the pH, and that produces acute respiratory alkalosis, but your kidneys work to excrete bicarbonate. And PaCO2 at high altitude, it achieves back to when adaptation is achieved. The pH is 7.4 and the PaCO2 is 30 millimeters of mercury. That's normal, totally compensated respiratory alkalosis or chronic hypocapnia, but this is a normal condition for high altitude. Total estimated population living about 2,000 meters in the world, more than 200 million people. So it's a big, big market and it's growing all the time. Is it possible that 200 million people are living in an acid-base status of compensated chronic compensated respiratory alkalosis? We answer that no, and the paper is written, is referenced down there. High altitude residents are living under normal conditions for their environment. Recently, arterial blood gases have been measured near the summit of Mount Everest, and these results have been published by Grocott. You see the PaO2 was 24 millimeters of mercury, pH 7.53, hemoglobin 19.3, and PaCO2 13.3. That was measured at 8,000 in this paper. This is the Fans-like equation where we evaluate the base excess or base deficit. It's the balance of pH in the organism. This is extremely, extremely important for cell function. And so what we did when I was a visiting professor in Copenhagen with Professor Paul Erik Paulev, we changed the name to THID, titratable hydrogen ion difference, which you're able to measure in the equipments, which is more efficient. There we are with Paul Erik Paulev at the University of Copenhagen. And so we modify this formula for altitudes. We consider the hemoglobin of altitude and include it in the formula, and the altitude bicarbonates also in the formula because we have lower bicarbonates as a compensating factor. And that way, the sea level Sigurd-Andersen acid-base chart, where you can see here the normal area is located up there. If you look at it right there, the oval area is the normal area, but it refers to a PaCO2 40 of 40. So we created charts for different altitudes from 2,000 to 3,000, 3,000 to 4,000 altitudes. And as you can see, that line keeps dropping down because at our altitude in La Paz, the PaCO2 is 30. And if we compare that for the 4,000 to 5,000, you see the difference between the horizontal line at high altitude in relation to sea level. And so you will see now that at Mount Everest, the level is much lower at 8,848 millimeters. If acute adaptation to high altitude is achieved and the acid-base status of blood changes and becomes normal with no alteration of base excess or negative base excess or previously known as base deficit, there can be no base deficit under normal conditions of adaptation to high altitude. In other words, complete acid-base adaptation to high altitude implies a normal acid-base status for that altitude with no deviations from the normal. These are extremely essential concepts for adaptation to chronic hypoxia. And so Grocott's data showed that, well, first of all, here's in the X scale, you have the barometric pressure. You see sea level is up here. And as you go up high, your barometric pressure reduces, and you see the different altitudes up to 4,500 meters. And that was the base deficit. This was the old terminology of base deficit and so on. And so they calculated this For that, they used the sea level values to calculate on the summit of Mount Everest what the acid-base status would be. And they calculated it to be 6.9 millimoles using the sea level values. Can an individual be walking around a mountain with such a base excess? This is somebody that's almost in intensive care, but these guys are climbing the mountains. So something was terribly wrong in the calculation. So we applied our THID measure, which is the modified high altitude fan slide formula. And this is the real acid base status of a subject at 8,400 meters. And this is why the extraordinary mountaineers are able to survive and continue to perform because they are in normal acid base status. The tolerance to hypoxia formula is a crucial formula we have developed. The hemoglobin is on top and the PaCA2 on the bottom, plus a time multiplied times a factor. And the top line is the oxygen transport mechanism of hemoglobin, and PaCO2 is the ventilation. This is extremely important, and it will play crucial roles later on in medicine and laboratory diagnostics. This is a graph to show that as you go up, the tolerance to hypoxia increases. For instance, at sea level, it's 1, but when you reach Mount Everest, you have a tolerance of almost 6 times, much more tolerance. And now, let me explain something here. This is the Crater Hab project, and this was developed by Dr. Akbar from Australia, by Marek Dynamics. These habitats, he developed all the technology for the resistance along with his colleagues, the technology to sustain pressure, because as I told you, in space, there is no pressure. So when you go to the moon, there's no atmosphere. You need to sustain the pressure for people to live in there. You have to create an artificial atmosphere. And along with an artificial atmosphere, here on Earth, we have the height of the atmosphere, which is the weight of all the molecules of oxygen, 20.9%, plus nitrogen and other minor gases that are at pressure that create the pressure that permits oxygen to go into our lungs. And so in this case, in Crater Hab technology, they have developed all the technology, they have all the patents, and with that, they are able to pump air into these habitats. That way, astronauts will be able to work, will be able to carry out life as though they were on planet Earth, but not at sea level. This is extremely important to understand, because when you want to create a small capsule and you pressurize it to have the pressure of sea level, you require a very thick cover to retain, because in a wall, we made an analysis when in our laboratories here in La Paz, we have a chamber, and I am perhaps we have some time. Yes, I can show you some of that chamber. Uh, one of the walls that was about 3 meters long and 2 meters high, when we were going to pressurize it here in La Paz to the sea level pressure, it would have to retain 52 tons of pressure. So when the environment becomes bigger, the pressure grows exponentially and becomes huge. For this reason, it is extremely important that the pressure for space habitat be the high altitude pressure of the city of La Paz. That way, the structures will be able to tolerate better. They will have a safe margin. And this means that high altitude residents will have to having the high altitude residents that we have here at high altitude in the city of La Paz and other areas of the world, in the Himalayas, in Lhasa, Tibet, for example, are adapted to this lower pressure. And that gives them an advantage in travel to space. Actually, in the near future, I can foretell that astronauts will come to the city of La Paz to train. It's a city where you can have all kinds of entertainment, all kinds of quality food, and you will be training because your organism has to adapt biologically. So I would, I can tell you that it will be a, a temporary station to travel to space. How long would they have to stay in the city of La Paz? That's a very good question. According to our studies, hematological adaptation takes around 40 days from sea level. When you come from sea level to the city of La Paz, it takes 40 days of adaptation for your red blood cells to increase logarithmically. I have left out most of these slides because I wanted to speak to you about these things personally and to show you these things. And, ¿sabes qué? Me he acelerado tanto que me sobra. And now we are going to apply this with Dr. Muhammad, uh, Dr. Hussein and Akbar, Dr. Akbar, applications in mining at high altitude. Because miners, when they go to work from sea level to mines at 4,000 meters, they suffer difficulties of adaptation because they have to travel up and down and up and down and so on. So we are going to create these habitats of mining at high altitude with pressure inside. And this is a very beautiful project we're developing with Dr. Akbar. Incidentally, he was here during our 9th chronic hypoxia, as was Dr. Professor Tupil Venkatesh and Dr. many other colleagues from around the world. And we discussed these things that are trending space things, and they mean the future of humanity. So I have some final reflections to make. Diagnostic laboratory equipment to be used at high altitude in space should be sturdy and be calibrated for high altitudes and space. Grok 4th and forthcoming ARs are a turning point in humanity. Where will it lead us? Opinions range from doomsday scenarios, AI wiping us out, to techno optimism, AI as our savior. All the education gathered by every individual over more than 16 years, school plus university, becomes practically useless. Memorization of information is a waste of time. A 7-year-old child can answer any question with the use of AI. In any case, neurons begin to suffer atrophy. Now, this is dramatic. What is the use of painfully studying for a PhD to be able to partially answer complicated questions in mathematics or in any other field if Grok can answer any question perfectly, 100% in a matter of seconds? PhD programs should reframe their teaching methods, stimulating above all creativity and all education, school and everything. But we have to train our neurons always. Otherwise, we will suffer atrophy in terrible changes. And biospace forming cannot be atrophy of us. It can be an evolution, positive evolution. Finalizing this presentation, I want to tell you that I have India in my heart. This is one of the reminders that I have so kindly received in your extraordinary country. You have a different frame of mind, and your progress in India is going exceptionally well. The great future. I am so proud to be part of India. I consider India my second country. And now I want to show you a little bit of my institute. I want to show you our beautiful city of La Paz, located between 3,100 and 4,100 meters. And you will see the cable cars that are right next to our institute, where they take us like the metro, but through the air. There you see them going up to different locations, 12 different stations, all the city. Welcome to the High Altitude Pulmonary and Pathology Institute, Happy IPPA. Come on in. And this is a pulmonary function laboratory. This is a plethysmograph, and here we do the respiratory studies. A lot of this software was developed by me, and this is a breath holding test with a typical curve observed, the M curve of breath holding in the saturation changes, and an spirometry. And for instance, my normal saturation here in La Paz, you can read it right here, 92% saturation. That's a perfectly normal saturation for La Paz. And now I want to show you our hyperoxic-hypoxic adaptation chamber. The version number 2. Come on in. So in this chamber, we can take you to sea level, or we can take you to Mount Everest. You see here we have a helmet, and we modify rapidly the concentrations, and you see all the sensors that are involved in this institute chamber. So I want to thank you for your attention. You are all of you welcome here in La Paz, Bolivia, whenever you want to visit. And it has been a great pleasure to share these moments with you. I send my great regards and hello to my very good friends in India. All of you, I cannot list all of you, but I have many, many good friends. Thank you very much.